Okay, so we're going to begin with section 7.1 in your text. This is known as the fundamental counting principle. Okay, what this does is it is a way to determine all possible outcomes. Here's an example. All right, so we're just going to pretend for a minute that you let your laundry get out of hand. You just have been busy and exhausted, and you have not done any of your laundry. So at this point, you have just 3 clean shirts left. Those clean shirts consist of 1 yellow shirt, 1 white shirt, and 1 blue shirt. You also have 2 clean pairs of pants left. One are jeans, and 1 pair are black. How many different combinations are possible? So how many different unique, non-repetitive outfits could you create? What do you think? It would be 6. And how are we getting 6? Right? Am I doing this right? And then 1 blue and black. So basically, you're just keeping room for every possible combination, right? Each of the 3 shirts can go with each of the 2 pairs of pants. Okay? We can say that this is the same as 3 times 2. We have 3 choices for the shirt times 2 choices for the pants, and that gives us 6 possible outcomes. Okay? This is known as the fundamental counting principle. It says, if you can choose one item from a group of M, where M is a number, and then we're going to choose a second item from a group of N items. Then the total number of outcomes is going to be M times N. Now, I've gone through it in like a laundry day type situation, but there are several different ways in which we can use this particular counting principle. Okay. All right. So in the notes, in 7.1 notes, in problem number 1, I have asked you, you have a single die, and a single die, standard die, has 6 sides, 1, 2, 3, 4, 5, and 6. Okay, and then I also have a spinner on the picture. That spinner is split into 5 sections, 2, 3, I think, yeah, 4, 5. And that spinner has, oh, I'm missing a row. Okay, that's fine. Spinner has a red, a green, a yellow, a blue, and an orange. Okay? So I've asked a couple of questions about it. First of all, how many different outcomes are there for a standard dice? There are 6 outcomes. You could roll a 1, a 2, a 3, a 4, a 5, or a 6. So there are 6 outcomes for the die. And based on this spinner, how many different outcomes are there for colors? There are 5 outcomes for this spinner. You could land on red, green, yellow, blue, or orange. Okay? So, I'll move this down. If you roll the die, and then spin the spinner, how many different outcomes are possible? No, the answer is not a fraction. I want to know that We have 6 possible numbers, and each one of those numbers could go with any one of 5 colors. So this is going to be 6 times 5, or 30 possible outcomes. Okay? We're just trying to get a sense of all the options right now. We're not talking about the probability of any singular option. We're just trying to get all possible. All right. So problem number 2 says, next term, you're going to take 3 classes. You can choose from any one of 5 health-related classes, any one of 5 nursing classes, and any one of 3 English classes. How many possible combinations? Now, this isn't saying they'll all work with your schedule. This isn't saying that they'll all work for you. I just want to know how many possible combinations there could be. Well, for the health classes, you have 5. For the nursing classes, you have 5. And for the English classes, you have 3. This gives us 5 times 5 times 3, or 75 possible outcomes. Doing better? That's all I'm saying. That this will give us all the possible outcomes. Now, Cole, I don't know if there's any conflicts in there. Maybe some of them run at the same time. Maybe some of them run during your work schedule. I'm just trying to get all the possibilities. Okay. All right. Let's try the third one. Okay, you're searching for a new apartment. You've settled on the perfect complex in Holman, and you have the following choices. You could choose a 1, 2, or a 3 bedroom. You could have 1 or 2 baths. You could have indoor parking, outdoor parking, or no parking, as in you don't have a car or don't need one. You could choose a balcony or not. And you could choose a fireplace or not. The question is, how many possible outcomes? each one of these is a choice, right? So how many bedroom choices do you have? And how many bathroom choices do you have? How many parking choices? Indoor, outdoor, or none. So you actually have there. Because, maybe you don't need a car, or maybe you're using your bicycle, or a little scooter. I don't know. All right. Yeah, so for like this balcony or not, I could get a balcony or I could go without. So that's actually two choices. I could do a fireplace or not. So that's actually two choices. And this isn't saying, Lexi, that always not is a choice. But if I'm looking at apartments and a balcony is going to raise my rent, I want to know if I have a choice between a balcony or not. Right? The same thing in some complexes with parking. If they've got like underground parking, it's one price. If they've just got a parking pad outside your apartment, it's a lower price. And if you don't need parking, they might take even more off. So yeah, this isn't about the pricing. It's just about the different combinations I could get. How many possible combinations are there? And if I just do that, I've got 3 times 2 times 3 times 2 times 2, or 9 times 8, which is 72 possible outcomes. All right, problem number 4 has us taking a quick quiz. In this quick quiz, you have 6 questions of multiple choice. Each multiple choice has 5 answers. The last 4 questions are true false. How many different outcomes for this quiz? Now this one's a little bit harder because you have to think about it in a slightly different manner. Nope. Nope to either of them. It's, yeah, no. I know why you think it's 6 times 5 times 8, but this is not going to work. You have to think of it slightly differently. If we're looking at question number 1, How many different outcomes are there for question number 1? So there are 5 choices. If you're walking into this quiz totally blind, you have 5 choices for problem number 1. How many choices do you have for problem number 2? Right? In other words, you could have picked A with A, you could have picked A with B, you could have picked A with C, you could have picked A with D, you could have picked A with, so we're just at 2 problems and we already have 25 outcomes. How many options do you have for problem number 3? What about problem number 4? And problem number 6? Oh, I forgot 5. Problem number 5 is also 5. Problem number 6 is also 5. Okay. And what about problem number 7 then? And problem number 8? And problem number 9? And problem number 10. Do you see how this is a little different? Because each question represents brand new choices. So this isn't 5 times 6. This is 5 to the 6. 5 times 5 times 5 times 5 times 5 times 5. And then I have a choice of 2 4 times. And if I do that on my calculator, 5 to the 6th times 2 to the 4th, I have 250,000 possible choices. Or possible outcomes. Nope, we wouldn't do 4 to the 2nd. 4 to the 2nd would indicate 2 questions with 4 choices. Exponent. And the number of choices on that question is your base. So 5 to the 6th tells me I had 6 questions with 5 choices each. And 2 to the 4th tells me I had 4 questions with 2 choices each. This is also interesting to me, just a quick little side note, because when somebody tells me they got 100 on the quiz and they guessed everything, I mean, if they got 100 on the quiz, that means they picked the one right combination out of 250,000. So, yeah, they got really lucky. Now, I mean, it's one thing if you guessed on 3 of them, but you knew the rest. Okay, that's a little bit better. But, yeah. All right, questions on that one? Emma, Stacy, are you guys okay on that one? Okay. All right. Number 5 is some safety. Where is it? There we go. Number 5 says your bank PIN. Many of us have a PIN number for our bank. Uses 4 digits, 0 through 9. How many possible outcomes are there? So this one is much like the question one we just did. So for the, nope, for the first number, how many possibilities do you have? Watch 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we're looking at the digits 0 through 9, there are actually 10 possibilities there. For the second digit, how many possibilities are there? It is. It is still 10. We put no restrictions on it. For the third digit, how many possibilities are there? Still 10, 0 through 9. And for the fourth digit, still, so this is going to give us 10,000 possible outcomes. Okay? Now, sometimes you know that banks will put restrictions on their passcodes. So, what if the bank does not allow you to repeat a number? So, in other words, the bank says, okay, you can have 0 through 9, but you can't use 2222. Well, let's talk. The first one would still be what? Okay, so the first one would be 10. But then on the second one, you can't use what you used for the first one, whatever it may have been, but the remaining 9 are still up for grabs. On the third one, you can't use what you did for the first one, but you also cannot repeat the second one. Since you cannot repeat a number, you can't use the same number twice, which means the 2 you already used are out. And this means that the fourth one, you would only have 7. That does leave us with 5,040 possible outcomes. But is it more secure? Some banks would say yes. Some banks would say we have way too many customers that make their passcode 1111. Right? And others would say no, because I can still use 1, 2, 3, 4. That's why some banks don't allow some of the simplest. All right, here's one. So how many 4-letter radio call stations can be found if the first letter must be a W or a Z. We see this in Wisconsin, right? It's Z93, WIZM. These are the call letters for the stations. Okay, so we're going to do a 4-letter radio call station. So we've got 4 of them. And how many choices do we have for the first letter? Well, the first letter has to be a W or a Z. How many choices is that? Yeah, so the first one is just 2. Now, the second letter can be anything. So, how many letters are in the alphabet? Yes, there are 26 letters in the alphabet. Our third letter can also be anything. And our fourth letter can be anything, also a 26. And that gives us 35,152 possible outcomes. Alrighty, what can I do to help? But only for the first one. The first letter must be a W or a Z. So that gives me 2 outcomes for the first letter. Yep. All the other letters could be any letter of the alphabet. Yes. Okay. All righty. Good. All right. Any questions on the fundamental counting principle here and how it works? Everybody seems pretty good. Okay. All righty. So that's section 7.1. And from there, we're going to jump to section 7.4. Which is the fundamentals of probability. The first probability we want to talk about is theoretical. Theoretical probability is probability where each outcome has the same likelihood of occurring. What do I mean by that? I mean that the dice isn't weighted. I mean that the coin has an equal chance for each side, heads or tails. I mean that your schedule is just as likely on a Monday as it is on a Saturday. Okay? That there's no sort of pattern or regularity. Now, this is known as theoretical because we're treating everything as being equal. In this case, P of E is known as the probability of an event. P of E, or the probability of an event, is determined by taking the number of outcomes of the event and putting it over, hello, hey, I'm coming. Sorry about that. Yep, that would be my guesstimate. Let me see here. Let me share this again. All right, is it visible again? Ooh. Okay. Okay. There we go. All right. So the number of outcomes of the event E over the total possible outcomes. All right. Okay. So let's take a look at a standard die. I think I just want to say die. There we go. A standard die, which we've done already, has 6 sides. 1, 2, 3, 4, 5, and 6. What is the probability of rolling a 1? Of the outcomes, only one of those is a 1 compared to the total number of 6 outcomes. What is the probability of rolling a number less than 7. Of all 6 of the events, all 6 of them are less than 7. So this would be 6 out of 6 or 1. What's the probability of rolling an even number? There are 3 even numbers, a 2, a 4, and a 6, out of 6 possible. This should reduce to a 1/2. What is the probability of rolling a number that is not a 3? There is 1 3 and 1 2 3 4 5 that are not 3.
Is equal to sum of the square on the other two sides. Why is a mouse?
You want to bet that's my mother? Oh, nope, it's not.
The answer to that one. The square.
All right, so that's 5 out of 6. Okay, questions on any of these? These are pretty good, right? Like, I compare this to, I call it socks in a drawer stuff. You've probably been doing problems like this all through grade school. There are 6 pairs of socks in a drawer. 3 are red and 3 are that kind of thing, right? Marbles in a jar, socks in a drawer. You've done lots of problems like these. All right, now, what does sometimes come into play is a deck of cards. I don't know how many of you are familiar with a deck of cards. Standard deck of cards. Yep. There is a graphic that I am perfectly fine with you using. It's in the notes, it's in the textbook, and it should be on one of the formula sheets. I'll try to remember to send it out. But it's absolutely possible for you to use the sort of tips or hints, if you would, for probability, particularly a deck of cards, because not everybody is aware of them. So yeah, it is a lot like blackjack, although blackjack is a little bit more complicated than some of the probability we're going to do today. We might get a little bit closer to it on Thursday, but yeah. So for this next group of questions, we're using a standard deck of cards. Okay, so given that you're using a standard deck of cards, determine the probability that you're dealt a heart. Oh, yep. What we expect that you know, or at least can determine from the graphic, is that when you look at a deck of cards, 13 of those cards are hearts out of a total of 52 cards. Now, this will reduce. This is the hard thing about a deck of cards, is that you can reduce it. And if you're unsure, you can use the fraction button on your calculator. See how I'm going to do 13 over 52? And that does reduce to 1/4. So my probability here is 1/4. Problem number 10 says, what is the probability that you are dealt a king? And so what we expect you either can determine or that you already know is that there are 4 kings out of 52 cards. And again, you check to see if this reduces 4 out of 52, and it does to 1 out of 13. So the probability of getting a king is 1 out of 13. Number 11 asks you for the probability of a red 7. There are 2 red 7s. One is a heart, one is a diamond, out of a total of 52 cards. And this will reduce to 1 out of 26. "12 asks you for the probability of a jack of clubs. Now, there are 13 clubs, but only one of those is a jack. So this would be 1 jack of clubs out of 52 cards. So that's just going to be 1 out of 52. Okay. 13 says, what's the probability that you get a face card? Now, that's a card with a face. That's a card with a face. So that's either going to be a jack, a king, or a queen for each of the 4 suits. Yep. So there are 12 faces on 52 cards. Which gives me probability of 3 out of 13. "14 says the probability of an even club. Even would be a 2, 4, 6, 8, or 10. And clubs, so that's 5 clubs are even on a 52. So that's just going to be 5 out of 52. What's the probability that it's not a 10? Well, hold up. These can be done in a slightly different manner. We can say 4 are a 10, right? So 52 minus 4 are not. So this would give us 48 not a 10 out of 52 cards, which is 12 out of 13. We can rewrite this as 1 minus the probability that we got a 10. Or 1 minus 4 52s, which is 48 out of 52. I like doing those that way because it's often faster. For example, problem 16 says, what's the probability that it's not a heart? I would do 1 minus the probability that it is a heart, or 1 minus 13 out of 52. And I'm just going to pull my calculator out here, right? And type that in as 1 minus 13 out of 52. And it's going to tell me 3/4. Which makes sense because there are 4 suits. 1 suit is a heart, 3 suits are not, so 3 out of 4. Yeah, that's like a 100%. It's like an all of them one. Okay. All right, I'm going to skip the Potter piece. Where am I time-wise? And then, okay, yep, we're good. I'll finish. Okay, so I'm going to jump a little bit. And I want to look at a slightly different probability because I know it does come up. I want to look at the probability of 2 dice. Okay. All right, so the probability when you're rolling a pair of dice, you have 6 outcomes on the first die, and you have 6 outcomes on the second die. This gives you 36 different outcomes. Now, this seems like a lot, but if we consider that our first toss could be a 1, a 2, a 3, a 4, a 5, or a 6, and that our second toss could also be a 1, a 2, a 3, a 4, a 5, or a 6. We have to consider that we could have rolled a 1 with a 1, a 2 with a 1, a 3 with a 1, a 4 with a 1, 5 with a 1, 6 with a 1 with a 2, a 2 with a 2, a 3 with a 2, a 4 with a 2, a 5 with a 2, or a 6 with a 2, a 1 with a 3, a 2 with a 3, a 3 with a 3, a 4 with a 3, a 5 with a 3, a 6 with a 3, a 1 with a 4, a 2 then a 4, a 3 then a 4, a 4 and a 4, a 5 and a 4, a 6 and a 4. Excuse me, a 1 and a 5, a 2 with a 5, a 3 with a 5, a 4 with a 5, a 5 with a 5, a 6 with a 5. Or I could have rolled a 1 on the first die and a 6 on the second, then a 2 with a 6, a 3 with a 6, a 4 with a 6, a 5 with a 6, and a 6 with a 6. The question sometimes comes up, is rolling a 2 with a 1 any different from rolling a 1 and then a 2? Are those different outcomes? Well, sometimes. Sometimes rolling a 2 and then a 1 is entirely different from rolling a 1 and then a 2. It depends upon the game you're playing and whether or not the order of the die matters. Sometimes rolling a 3 first and then a 1 is a different outcome from rolling a 1 first and then a 3. And again, sometimes it's not. Now, I can see when I write this out all 36 different outcomes. It's not fun, but I can see them. Right? So when I can see all 36 different outcomes, I can ask some probability questions. For example, problem 19 said, what's the probability that you've rolled 2 even numbers? That means I have to look through my data, all of these different outcomes, and circle all the ones where they're both even. So there's 1, 2, 3. They're not going to both be even here. 4, 5, 6. This is an odd number, so they're not going to both be even here. 7, 8, 9. So when I look for 2 even numbers, I had 9 possibilities with 2 even numbers out of 36 possible outcomes. This gives me a probability of 1/4. I can ask for a different set of outcomes. What's the probability that the 2 numbers have a sum of 9? So now I need to ignore all of these that I just circled, and I only want to count up. I only want to include them if when I add the digits, I get a sum of 9. So that would look like my 3 plus 6 is 9, 4 plus 5 is 9, 5 plus 4 is 9, and 6 plus 3 is 9. So here I got a total of 4 out of 36. The probability here is 1 out of 9. "23 says what's the probability of a 5 on the first roll? So that means I'm going to get rid of all of these now. And I only want to pay attention to the ones that had a 5 on the first roll. Well, there's my first roll. 1, 2, 3, 4, 5, 6. And I have a 6 out of 36, which will reduce to 1/6. Problem number 24 says the probability that you rolled a 2 and a 6. Well, the probability that you rolled a 2 and a 6 does not dictate any order. It just wants a 2 and a 6 together, both a 2 and a 6, which would mean this one, but could also be that one. A 2 and a 6, a 2 and a 6. They're both there. So that's 2 out of 36, which is 1 out of 18. This is a different outcome than problem number 26, which states the probability of a 2 and then a 6. Do you see how that's much more specific? This one says we're going to start with a 2 and then roll a 6. So that's a very specific outcome out of the 36. There's only one of these outcomes that is a 2 first and then a 6. Questions for me? Everybody all good? Okay. 25 says a 3 on the second roll. That one would be just like a 5 on the first roll. So if this is your first roll and that's your second, we'd only want 3s in the second column. So that would be 6 possibilities out of all 36. Okay. 22 is a little interesting too. 22 says two numbers whose sum is 15. So 22 is the probability that you had a sum of 15. Considering the largest would be 6 plus 6, and that adds up to 12. The chance that you would have a sum of 15 is a big old fat 0. That's not going to occur. Right? Since the biggest one would be 6 plus 6, and that's 12, we're never going to reach a sum of 15, not for the two of them. We'd need to have a third die in there for that one. All righty? Okay. All right. The other probability I'm going to spend just a couple minutes on is called empirical probability. Empirical probability is probability based on observable outcomes. Sorry, it went away. Let me get it back. Nope. There we go. Okay. All right. So it's probability based on observable outcomes, meaning the probability of any event is going to be equal to the observed number of occurrences compared to the total number of observations. Okay, these are often based on data collection rather than like the sides of a die or something like that, rather than something tangible. They're often based on some sort of data collection. For example, I have a chart here that compares male and female graduation rates. In terms of their education. So we're going to look first, we looked and took some data on the number of people that had less than 4 years of high school. So the number of people that maybe dropped out or were forced out of high school before they were able to graduate. And then the number of people who had 4 years of high school. Then we looked at people with some college. So they did go to school, but they did not graduate. That would be my dad. He always jokes. He graduated in drinking, he says. All right. And then somebody who had 4 years of college or more. And then we'll look at this last row will be totals. Whoops. Okay. All right. So when we looked at the males, we had 14 males with less than 4 years of high school and 15 females. That gave us a total of 29 people that had less than 4 years of high school. 4 years of high school only, we had 25 males and 31 females, giving us 56 people that had 4 years of high school. People who had some college, 20 were males, 24 were females, giving us 44 total people that had gone on to some college. And when it came to 4 years or more of college, we had 23 males, 22 females, for a total of 45 people with 4 years of college or more. All told, that meant we had 82 males sampled and 92 females sampled. That's a total number of 174 people. Okay, so we're now going to use this data as empirical probability. We're going to take this data set and figure out the probability for this particular population. Problem number 27 asks, find the probability that a person in this sample had less than 4 years of high school. So we want to look at the observable total for less than 4 years of high school. How many people did we observe that had less than 4 years of high school? Twenty 29 people would have had less than 4 years of high school out of our entire sample, our grand total, which was 174. Now, sometimes these will reduce. So I'm going to do 29 out of 174. I'm going to see if it reduces. And it does to 1/6. I should mention, I'd be remiss if I missed, this can also be done as a percent or as a decimal. I can do 1 divided by 6. This is the same probability as 0.16 repeating, which is a 16.6%. All of these are ways that you can write the probability. As a decimal and as a percent. Now, the vast majority of what this particular textbook uses is the fraction, which is why I haven't stressed the other two. The fraction is usually what we will see. "28 says the probability that they had 4 years of high school. There are 56 of these people out of 174. So will that reduce? 28 out of 87 as a fraction, which is going to be the same as 0.3218, or about the same, which is about 32.18%. Right? It just kind of depends upon what you want. Oftentimes when you get an answer like 28 out of 87, they'd much rather say 32%. Right? Because 28 out of 87 is not sort of a number that makes sense or that's easy to visualize, maybe, but 33% is pretty easy to visualize. All right, probability that they had 4 years of college given they're female. Okay. We'll do more of this later, but this is very specific. This is asking you had 4 years of college given they're female. So this part right here, this given female part, tells me that I want my denominator to be just the females. Yeah, so on the numerator, I'm going to look at 4 years of college and female, but the denominator, I just want the females, because given female tells me I'm ignoring the male population for this one. So this would be 22 out of 92, which should reduce. 11 out of 46, which is a 0.2391, or about 24%. No, I just want the 4 years of college. Oh, but yes, I would take it out of, you missed, this 92 is the total number of females. So if I didn't have that total, then yes, I would have had to add up the 15, the 31, the 24, and the 22. Okay. All right, one more, or are we good? For number 30, it would be the 20 from the sum college and male out of 82, which is the total males. Yep, correct. The hadn't completed high school, they're referring to the less than 4 years of high school. No, 31 and 32, that's a good question, Lexi. Do you see how 31 says given they were a man? So that's going to be out of your male total, which is 82. So 31 would be less than 4 years in male, so 14 out of the total of 82, right? However, 32 says there were a man given they didn't complete high school. So since their given was they didn't complete, it would be out of 29. So if we're looking at the difference there, number 31 would be that 14 out of 82 versus number 32, which would be the same 14, but out of 29. And this is how they can get you, right? Because if we look at men that didn't complete 4 years of high school, we're looking at 17%. But if we're looking at those that don't complete high school, 48% of those are men. And it sounds like we're talking about the same thing when we're not. So that's just that probability and where it gets you. But this is all I had on the agenda for today. This was 7.1 and 7.4 in full. I didn't skip over much of anything, and I didn't leave anything out. So, are there any last minute questions? Everybody's pretty good? Yep. Yeah, we have one more test coming up. That test is not for a few weeks yet. So, nope, we ditched the final. Yeah, it's just one more thing off your plate. That's all we were trying to do. Nope. We have a lot on our, all of us have quite a bit on our plates right now. So um, we didn't take out a lot, but we did take out the final for this class. So okay, all right. Yep, 7.1 and 7.4 are due on Friday. I'll be here Wednesday doing 7.6 and 7.7 and answering any questions you might have from 1 and 4. 7.7, 7.6 and 7.7. Yep. Okay. All righty. You're welcome, guys. If you have any other questions, you know how to reach me. Thank you. You too. Bye-bye. Thanks, Emma. You too. Bye, Cole. Bye, Stacy. You take care of yourself and your fam, okay? All right.